Hello everyone, today's presentation is going to be about analysis and reduction of models using Persalys. I am Claire Leterrienne-Gérard from Chemical Engineering in France. The purpose of this presentation is to create a meta-model from a Modelica model. Meta-modeling and model reduction are synonyms, only they arise from different contexts. Meta-modeling is more statistical, whereas model reduction is a more industrial term. In this talk, we are exclusively going to use the term of metamodel. To reach this goal, we will first discuss the Modelica case study, then select its most influential variables, and finally proceed to the metamodeling step. We will also have a little bit of fun and go beyond Persalys' normal use by inserting the metamodel into a Modelica GUI to connect it to other components. So first, let's talk about the model we are going to work with. We have taken a case study about parabolic solar collectors. So these solar collectors, they do enable power production at an industrial scale just from solar energy. So as you can see on this scheme, the collectors are parabolic mirrors which gather the sunlight and reflect it onto an oil pipe, which is called here receiver. In this pipe, the oil heats up and reaches about to 400 degrees, and then in a power plant, the heat is going to be transformed into power, electrical power meaning. We focus on these parabolic solar panels and model them using Thermosys Pro library. So Thermosys Pro is a thermodynamic library for designing power plants, which is developed by EDF. So here you can see the model. So we have three inputs: the atmospheric temperature, the sun radiation, and the sun angle incidence. These four inputs arrive in the model of the solar collectors, and under we can see a heat exchanger wall linked to an infinite source of temperature, which mimics an infinite flow of oil through the pipe. So here's the model we're going to deal with. More precisely, we are going to consider as output of the model the heat flow transmitted by the fluid, so by the hot oil. We are going to look closer to 9 variables of this model and study their effect on the output. So these 9 variables belong to 3 groups approximately. So first variables are geometric, so they correspond to characteristics of the solar collector and or to the oil pipe. So there is, for instance, the length of the tube, the angle of the mirrors that do more or less wrap the tube. There is the focal length of the mirror and the transfer coefficient of the mirror to the pipe. We also have kind of cleanliness parameters, so meaning parameters that can be affected whether the mirror or the pipes are dirty. So these parameters are the reflectivity of the mirror and the transmittivity of the glass in the pipe. And last variable group is the weather. So as mentioned before, the atmospheric temperature, the incidence angle of the sun, and the sun radiation. So what's at stake there? Between studying the link between these 9 variables and the model output, first stake is model understanding. We are interested into knowing which are the most influential variables in order to get better insights in the model behavior. Another stake is the model simulation speed. Knowing the most influential variable, can we actually accelerate the simulation of the model using, of course, a meta-model? To do this, we are going to consider all the variables constant during the simulation. This means that our physical model, or Modelica model as seen before, is going to amount back to a function with 9 inputs and 1 output. So as parameter and inputs are actually Modelica types, I will try to employ as much as possible the term of variable for the statistical analysis, so as not to mix words. So we're gonna do all this using Persalys software. And it's gonna be pretty easy. So to present you a little bit Persalys, it's a software for probabilistic and statistical analysis of physical models. These models can be OD, 1D, or finite element models, both work. Technically speaking, this software is a graphical user interface based on OpenTURNS probabilistic and statistical methods. So for those who know OpenTURNS, it is a probabilistic library for the treatment of uncertainties co-developed by Fimeca, EDF, Onera, Emacs, and Airbus. Anyway, Persalys is also developed by Fimeca and EDF. Technically, it's a free software, and it's designed for non-specialists. So do not hesitate to just give it a try. You can download it on the website for both Linux and Windows. So what are the advantages of Persalys? There are, I think, two main advantages. First, it avoids having to write any code. You don't have to write Python code, you don't have to understand OpenTURNS samples. You just use a graphical user interface. Second best advantage is that it guides the user during statistical analysis. And so even though you are not a specialist, even though we are not specialists, we can use it and we can have results. Here you can see the homepage of Persalys, which is going to be the guide for statistical analysis. It works a bit like a video game. You have to cross levels from left to right, and you cannot reach the higher level if you have not crossed the levels in between. So in here, you can see that we have defined the model on the left, so we have access to model evaluation, screening, optimization methods. But we don't have access, for instance, to calibration methods, because we have not set up the observations. As we have defined the probabilistic model on just under, you can see that we have access to methods such as sensitivity analysis, central tendency. Yet we cannot yet perform reliability because we have not defined a limit state. So what we are going to do from now is first perform sensitivity analysis. Using this, we are going to know the most influential variables on our model. This is going to be useful first for our understanding of the model. And second, knowing the most influential variables, we are going to create a meta model. Also, we can say it's a synonym that we're going to reduce the model in order to have a Python model which can run with an increased speed. All right, let's go then. So at first, we exported the solar collector model from the Modelica language to an FMU. This FMU is a format model exchange, yet it has no importance. It could have been co-simulation also. Persalys supports both. So we import the FMU in Persalys, and we perform first a screening. So by screening, I mean the Morris method. And this screening provides us with first information on the relative influence on variables. You can see here, the more right we are, the most important the variables are, the most influence they have on the output. The higher the variable is, the more nonlinear effects it has, or the more interaction with other variables it has. So we can see that the sun incidence angle and sun radiations are the most right, so they are very important variables, very influential variables, let's say. Also, the focal length of the solar collector, the reflectivity, and the rim angles are, let's say, more right than the big pack of variables on the left. So they are quite influential also. To continue, we are going to fix the 4 less influential variables to their default value. Their default value is defined in the FMU, so we do not have anything to do, just fix their value. And we are going to refine the sensitivity analysis considering only the 5 most influential variables, which are highlighted in yellow and we have mentioned before. We will refine the sensitivity analysis using Sobel indices. To rapidly explain what Sobel indices are, let's say that the first order index, accounts for the proportion of variance that can be accounted by each variable. So for instance, if we see here the incidence angle, its first order index is 0.3. It means that 30% of the variance of the output is actually explained by the sun incidence angle. We can also see that the radiation has a high first order index. It explains 40% of the variance of the output. As a reminder, the output of the model is the heat flow generated. And the other variables are pretty little influential in comparison. So we are going to consider that our two most important variables are the incidence angle and the radiation. Our purpose was double. First, to understand better the model. So here we succeed. We have seen that the sun variables are actually the most important. It has more influence to have the sun at the zenith or as going down, let's say, than having a higher reflectivity of the mirror. So we have understood better the model, yet we still want to reduce the simulation time of our model. So to perform meta-modeling, we are going to keep only 3 of the influential variable that we have seen. So we are going to keep the 2 variables of the sun incidence angle and the sun radiation. Also, and it's a choice, we are going to keep as varying the mirror reflectivity, as we know that it evolves over year depending on the cleanliness of the mirror. So we consider a model with 3 variables and 1 output. And we are now ready to create a meta-model out of this. Differently saying, we can now reduce this model. We also do it using Persalys, and you can see here the curve fitting of the cross-validation. If all the points are on a line, it means that on the exact line, it means that the meta-model is perfect. It's not perfect, yet we can see that the accuracy of the meta-model is satisfying. And when the execution time of the normal Modelica model is 10 power minus 3 seconds, the execution time of the meta-model is 10 power minus 5 seconds. So the meta-model is 100 times faster than the Modelica model. And this can be precious, especially to do statistics afterwards when a large number of simulation is required. So till here, in brief, we have seen that sensitivity analysis has enabled us to target the most influential variables. We have created a meta-model that is 100 times faster than the Modelica model. And this meta-model can replace the model for further statistical study, such as uncertainty propagation, reliability, and so on. So this meta-model can be used for statistical study, yet it cannot really be used in Modelica environment. It cannot be connected to Modelica models. And that's where we are leaving, let's say, the stroll in Persalys. Everything till here was fairly easy using the software, and I was curious, so we just went into the wild and tried to include the meta-model into Modelica modeling environment. So why do we want to use this? First, because it can be very practical to employ a meta-model and connect it to other Modelica models to go to large-scale models. The stake is to use meta-models from different modeling tools in the same simulation environment. And how do we do this? We basically create a Modelica wrapper that is gonna call the Persalys meta-model. And here you can see the result. I'm not extending on all the technical details. You can see here a thermal power plant from Thermosys Pro library. And you can see on the top that the normally solar collectors have been replaced by the meta-model we just created before. So you can see here as input, we have the sun incidence angle, the reflectivity of the mirror, and the sun radiation. The incidence angle and the reflectivity are fixed, whereas the radiation evolves over time. So To turn to a conclusion, we have showed in this presentation the easy use of Persalys to perform statistical analysis of an FMU. We have also had an exploration part to include a OpenTURNS metamodel, OpenTURNS and Persalys being the same in this case, in the Modelica simulation environment. So special thanks to Julien Schuller from FIMECA for adapting the library OTFMI to these needs, to Hubert Lervac for the Modelica modeling and especially on the thermal power plant, and on Daniel Busquela for his help and support on the use of ThermoSysPro library. Thanks a lot for your attention.